SolidWorks Simulation Lecture 6, Composite Materials. Open the part file. On XY plane, enter sketch mode, draw a rectangle. Make it 100 by 100. On surface toolbar, choose planar surface. I'll make the geometry as simple as possible so we can concentrate on CAE analysis. This problem is a composite panel, a 8-layered carbon epoxy composite. So the material property is the most important part. To prepare for the study, I need to load or add in the program here. Load the toolbar. And arrange the toolbar. So I have finished with the 3 preparing steps. For step 1, I open a study, which is a static 3D study. Remember that this is a composite analysis, so it is an orthotropic material. So the most important thing is to define the material. I have finished with the first step, which is a geometry and opening of a study. The second part is the most important material. And before I proceed with the second step, remember that this geometry is not finished yet because there is no thickness. So I have to define the thickness part. So for orthotropic materials, there are 2 types of orthotropic materials. One is homogeneous, one is non-homogeneous. For example, composite is not homogeneous, it's layered orthotropic material. So if you are going to analyze a homogeneous orthotropic material, then the story is different. You might have to choose thin or thick plate instead of composite, but the material part is similar. So I'll go ahead and define composite. Composite material, I'll choose 8-layer composite, 8 layers. I'll define it as symmetric composite. All panels are the same material. You don't have to choose this one, but for this case, all the materials are carbon epoxy composite. So I define material. And I will define a new material in any of these items, or you can define a new library, and then in the new library you define a new material. So I have already keyed in the numbers here. I defined a new material called T300. This is a very popular carbon composite in the market, and the properties can be found in Google here. So I have already defined the material, and this is my material. You can take a look at the properties. The most important thing is that you choose orthotropic instead of isotropic. Isotropic means the properties are the same in all directions. Orthotropics defines as that the properties are different in all directions, in x, y, z directions. So I have 3 Young's modulus, 3 Poisson's ratio, 3 shear modulus, and also I have to enter those strength, compression strength, and shear strength. And for density, it is close to 1.8, and the data sheet say it is 1.76. So this is the properties. Okay, so I have material properties keyed in. So when you are implementing this, you have to define a new material. Okay, when you enter the self-defined material or customized material, you have to new a library, and or in any of the existing library, you new a material, and you can call it T300 and enter all the numbers in the data sheet. Okay, so these are the numbers. Okay, I apply this material. So these materials are all T300, and for this panel, this is the X direction. So the angle is 0 degrees. For the second layer, it is 45 degrees here, like this. And for the third layer, minus 45 degrees. And the fourth layer, 90 degrees. And because it is symmetric, so the fifth layer, layer 5, is the same as layer 4 in the fiber direction. And also, fiber direction of layer 6 is the same as that of layer 3. And layer 2 have the same direction as layer 7. So the top layer and the bottom layer are all in the same direction. So you can see the top layer and bottom layer are all 0 degrees, right? So this is the most important part in this lecture, the material part. Once you have finished with the second step, the others are all the same. You define the mesh, hide the mesh, boundary conditions are claim the two edges, and apply a load here, 100 Newton. Okay, I'll implement the analysis. So this is the result, but this is a composite panel, so you have to define which layer this is, because this is layer 1, the top layer. You can also show the stress for layer 4, which is the layer at the center, but it is not right, because one of the sides have to be not stress-free. So this one thing, you have to edit definition and choose from the advanced options. You choose 3D rendering. Okay, so you can see that at the center ply, or the fourth layer, the stress is like this. The neutral surface is stress-free, but at the bottom it is not stress-free. And also, if you look at layer 3, both sides are with stress. It is not stress-free. So if you go to the top layer, layer 1 or layer 8, the stress is largest. So this is correct. So remember that if you use the options of 2D simulation, the stress might not be correct. It could be wrong. For example, as I showed you, if you show layer 4 in 2D plot, both sides are stress-free. It is wrong. It is not right. So you have to look at the stress in 3D rendering in order to show that these two faces have different stress. The stress conditions on the central surface is 0, and there got to be some stress on the low end here. So this is very important. For displacement, you also can define a 3D rendering, because in this particular problem, the thickness is only 0.8 millimeters, so it is very thin. You can barely see the thickness. It is very thin, right? but the thickness is there. Okay, so this is the lecture 6 composite material.